Homework solution 2.5. A freshman student has created the following power triangle to represent the given circuit. The student is confused as to why the circuit doesn't dissipate 7 milliwatts of power. Explain to the freshman what's wrong with their understanding. So the given in this problem is just these figures, and we're just asked to explain to the student what's wrong with their understanding. So I'm not going to really write those down. I am going to make the following observations, though. From the problem statement, we know that the magnitude of I is equal to 1 milliamp. And so we see that we've got 1 milliamp. There's 3 volts dropped across the resistor. There's 4 volts dropped across the capacitor. We can use this information to determine what the actual values for the power triangle are. And we're going to do that by saying that the power across the resistor is going to be 1 milliamp. So the magnitude of the current through it times 3 volts. So that's 3 milliwatts. And we know that the reactive power through the capacitor is equal to 1 milliamp times the voltage across it, 4 volts. So that's going to be 4 milli, not watts, but vars. We know that the purely reactive elements of capacitors and inductors don't create watts, they create vars, because this 4 is 90 degrees out of phase with this 3. So the total circuit power is not given in watts, instead it's given by apparent power, which is the complex sum of P and Q. And to indicate that they're out of phase, it's P plus JQ. So we get 3 milliwatts plus J, 4 millivar. We have to determine what the hypotenuse of this triangle is, and that is that S is equal to root of 3 squared plus 4 squared, which as depicted here is equal to 5. However, the unit for the apparent power is not watts or vars, but instead volt amps, VAs. Usually this is just said VAs, not volt amps. Or sorry, usually this is said volt amps, not VAs. So we've got watts, vars, volt amps there. Of these, only one is real power, and that's that 3 milliwatts. So you need to explain to this freshman student that the misunderstanding that they have is that resistors consume real power. Reactive elements don't consume real power. Instead, the power oscillates into and out of the component, and we annotate for that by calling them vars. The combined real and reactive power gives you a phenomenon called apparent power. They don't directly add. Instead, you have to use the same rules you did when analyzing impedance values. For this problem, I multiplied current magnitude by voltage magnitude for each of these. There are other ways to solve that. You could have used the v squared over x, or you could have used I squared times x, and same for the resistance. So multiple ways. And I encourage you to solve those the other ways for yourself to see that the different formulas for calculating power, and by those I mean power equals I times V, that they equal I squared R, and that it equals V squared over R. Those are the 3 kind of classic power formulas that applies to both Q and P if you use the values that are associated with the single elements there. So I encourage you to practice that.